we got to something like week 8, I think, or something like that. I don't know how many weeks we've done. We looked at the ideal transformer last week. What we're going to do now is we made some assumptions about the ideal transformer. Now we're going to look at how a real transformer differs from that ideal scenario, with a view to developing a model of a transformer, a circuit diagram model of a transformer that will take into account the losses involved in a real transformer, so we can do an analysis on a real transformer. That should culminate in us doing an analysis on the transformer on the rig there, see if we can predict how it would react under load, something quite close to full load. Okay, so practical transformers differ from ideal in a number of ways. First of all, the windings that make up the primary and the secondary, they have some resistance. So our ideal transformer, we didn't consider that at all. Okay. Secondly, the core of the transformer, the iron core that makes up the magnetic circuit of that, is not infinitely permeable. What that means is the assumption made with the ideal transformer is that it is infinitely permeable, i.e. we can go on adding more magnetic field and that will keep getting stronger and stronger. And that's about increasing the current or the number of turns. A real core will eventually saturate. Think of it like a piece of pipe, and you're trying to cram these lines of magnetic force into that piece of pipe. Eventually it will become full. So you can't go on adding more and more current and expecting that field to get stronger and stronger. Eventually it will saturate. So if we look at a graph of the magnetism going, we call that B, and this is H in a BH curve for a transformer core, our ideal assumes that we carry on adding amp turns, we carry on getting a stronger and stronger field. In reality, what happens is it hits a point where it saturates, and you can go on adding current and adding turns and it won't come back. And you might have seen this defined where we talk about another one of these losses, the hysteresis losses, when it comes back down again, because remember with the transformer it's AC and we are magnetizing it in one direction, then back and then in the other. That area in there represents a loss, because when we turn it all the way off again, there's some magnetism left that we need some reverse current to get rid of before we start creating a field in the opposite direction. So you get what's called a hysteresis losses in a transformer. Okay, so they're not infinitely permeable, they do saturate. So close to full load, you're going to be getting close to saturating your magnetic circuit. Third main thing on here is that the flux produced by the primary will not be completely captured by the secondary. So not all the flux created in the primary coil is actually going to be available to induce voltage in the secondary coil. Therefore, you've got some leakage flux that we need to represent. And there's leakage flux associated with the secondary coil as well, because there's a mutual thing. Okay. Fourthly, the iron cores produce eddy currents and hysteresis loss. So I've sort of explained what I mean by hysteresis loss. Eddy currents is a build-up of electrical currents within the actual iron core, and we use a laminated core I talked about last week to help to try and prevent that, where the iron core is made up of a number of steel plate laminations insulated from each other. That's an effort to restrict the amount of eddy currents that build up, but these are going to manifest themselves in heat and therefore become a power loss to the system. So we need to try and represent them somehow. Okay? Because all they're going to do is make the damn thing get hotter. So we want to develop a model of a real transformer that will take into account all or most of these attributes. And that way we can more accurately model what a real transformer is going to do. Ironically, once we develop this transformer model, we actually end up simplifying it again under certain conditions for a real transformer. Okay, but more about that later on this session, or probably start our next session. To represent the ideal transformer that's got an imperfect core, i.e. we're going to look first at representing the core losses. That's the heating of the core, okay, and what it takes to magnetize that core as well, the magnetizing current. Okay, so what we've got is that the core of a real transformer we discussed is not ideal. It's not infinitely permeable, and the hysteresis losses, eddy currents, cause heat power loss. But what this means is, if we've got a transformer connected to a supply here, even when the secondary is open circuit, there'll still be some current flow. That's this I.O. here, flowing the open circuit primary current. I2 will be 0, this one, because there's no circuit in that side. So although you'll measure a voltage here, let's say 110 volts, no current's flowing because it's not a closed circuit. But despite there being no current flowing in the secondary, a real transformer will have a current flowing in the primary. And what we've got is this current here made up of these two components through XM and RM. Okay, the RM is the current representing the core losses due to heating, or the power loss, so it's going to dissipate watts because it's a resistor. Remember what we've always said, it's only the resistors that will do real work for you, in this case generate unwanted heat, but they are actually using power. Okay, the XM is representing the magnetizing current needed to magnetize the core. So there's that. RM represents the iron losses and the resultant heat produced, which causes the in-phase portion of I.O. to flow, called IR. That's that current there. Okay, the in-phase current. Now, if we assume that the applied voltage is the in-phase component, IR is in phase with that. Okay, so if this is 600 volts, to go off the thingy pen, this is 600 volts, angle 0 degrees, then that current, because that's through a resistor, is also angle 0 degrees, that these two are in phase. The secondary voltage also must always be in phase with this voltage there. Those two must all also be in phase with each other. Okay, now XM, that represents the magnetizing reactance of the primary coil, produces the primary flux θ1. This requires a magnetizing current IM. That's the out of phase component of I.O., that one down there. So that's 90 degrees out of phase. Okay, and if we look at civil, yeah, we've got an inductive circuit, it's an inductance, the current is after or lagging the voltage. So that's a little bit of a check, but that current must be 90 degrees downwards, or a negative 90 degrees for that current. The resultant, this one, in there, IO, is a complex current made up of these two currents, IM and IR. Okay, and that's what's often called the exciting current. It excites the transformer, gets it working, if you like. That's what the meaning of the word is there. Not that it's an exciting current, but it's the exciting current, the one that will flow regardless of load. Are you all okay with that so far? Danny? Yeah? So, let's have a look. We'll have a look at an example. Large transformer operating at low load draws an exciting current of 8 amps when the primary is connected to a 400 volt 50 hertz supply. So we've got an IO there of 8 amps. This is 400 volts. A wattmeter test. It is known that the iron losses are equal to 500 watts. So PM is 500 watts. Calculate the reactive power absorbed by the core, the value of RM and XM, and the value of IR, IM, and IO. So, wanted to give some thought to how you might tackle that question. Right, what do we reckon then? That diagram on the right there is essentially what we're heading for. We want to calculate the values for those two components and hence find what the makeup of the currents. Where can we make a start with this, with what we've been given? What could we calculate? Via what method? $400. Yeah, 8 amps is what's flowing here, Tom. Yeah? Not what's flowing there. At this point here, that's going to count, that 8 amps has got to split 2 ways, isn't it? Yeah? You could actually calculate that at this stage. I mean, that's not the way that I've done it in my solution. But you could use the 400 volts and the 500 watts to calculate it. So should we go down that route? Because I don't, with these exercises, you're not forced to stay in the order the question's been asked. Okay, so Matt, how can we do it? You tell me the formula. We ain't got the cut. We haven't got the. If we're going to use this resistor is dissipating 500 watts. So it's just that resistor that's dissipating that. So all we can do is focus just on that resistor. So what do we know about that resistor? We know its power is 500 watts. What else do we know about it? It's got 400 volts across it. Yeah, because the two components are in parallel, we can use the voltage and the power to find the value of the resistor. Yeah, and the way I've done it, but you can do that. So what's the formula? So we're going to find R first. R, Rm. I don't care which order we find the stuff in. What's the formula? We got three versions of the power formula, haven't we? What are they? I squared R, we can't use that because we ain't got the current. Volts times current, we ain't got the current, is P is equal to E squared R. Yep. Therefore, R is E squared over P, 500 squared, 400 squared over 500. Let's hope that gives the same answer as my worked example that I got here. That come out as 320 ohms. Is that what you guys got? Yeah? Alright. Let's write on here 320 ohms. So what else can we find? Yeah. Therefore, IR is equal to 400 over 320 equals. Yep. What else can we find? Yeah, we can do that by what, Matt? What law is that? Yeah, so we'd say by Kirchhoff's current law, IM is equal to IO minus IR. That's 8 minus 1.25 equals. There's a problem with that. I want you to tell me what that problem is. You haven't taken into account that these two currents aren't in phase with each other. Okay? So that's not the right method. You can't do it that way because the 8 amps is a complex current that you don't know the angle of because it's made up of a horizontal component, IR, and that component that's complex, IM, is a vertical component, isn't it? Yeah. So although you know the magnitude of IO, but you don't know the angle, you're going to have to find that from finding the other two. So we need a different method to find IM. Look at how we found IR. We done it by voltage over the impedance or the resistance. We might be able to do. Is there a way to doing the IM in a similar way? Is there a route? What I'm saying here is is there a route with the information we got to find the value of Xm, the inductive reactance? Looking at how we've found the resistance, we've used the voltage squared over the power. What's the reactive power called? What letter do we use for that? Q, for the vars, right? So if we knew Q, we could put Q into this formula here, make it Q is equal to E squared over Xm, and rearrange that. Yeah? But we haven't been given Q. Is looking at what the information you've got, is there a way you can find Q? Yeah. So find the apparent power S and use the power triangle to find Q. So I'll leave you 2 minutes to do that, and then we'll add it to what we got on the board. Right, you got a number. What have you done then? How do we find S? Which is 8 times 400, 3,200 VA. Yep. Yeah.
X squared equals E squared plus B squared. So I've rearranged that.
Yeah. So we're in a boat of just writing this one out now, aren't we? Q is equal to.
Yeah. So Q.
Go on.
Just want the number.
Yeah. Now I want you to tell me the formula.
Q is equal to X squared minus B squared.
Correct. All square rooted. Yeah.
Yeah. So I've got 316 over.
So that's 3,200 squared minus 500 squared, and your answer? 316 over. Yeah. Mine rounded to 316. I got 3161, but I haven't got to worry about that. That'll do. Yours is right to 3 significant figures. Yeah. All happy with that? Next bit.
Figure out Xm with Q equals B squared over Xm.
Therefore,
3160 over 500 squared equals Xm. I'll rearrange that, sorry.
okay, yeah. Therefore, Xm is equal to E squared over Q. That's equal to 400 squared over 316. So is that what you've done?
Yeah.
Equals
7.
ohms. Yep. That's more or less what I got. Now we know Xm. What else can we find? So we're looking at our list of asks. We've got that. We've got that. We've got IR. We've got the reactive power. That's Q. We just calculated that. So do you see why I asked for that first now? Because we needed that to find Xm. But don't really matter what order you do them in. So last bit is what? Yeah. I am. What do they equal? Must equal E over Xm, which is 400 over 50.7. Yeah. Ah, 7.9 amps and 1.25 amps make 8 amps, because that's Kirchhoff's current law. What's the check here that we got those two currents right? .29 by Kirchhoff's current law. So we're going to check. That's why I've asked you to calculate IR and IM. Should add up to IO, shouldn't they? 7.9 plus 1.25 is a long way off 8 amps. Well, yeah. What we got to do is say IR is equal to 1.25 plus 0J, isn't it? Yep. Remember? IM as a per reactive current, so it must be 7.0 minus 7.9J amps. Those two added together gives us an IO of 1.25 minus 7.9J. And then if we convert that to polar, what do we get? Minus what? Yep, that's the unknown angle of that magnetizing current. And if you look at it, the reactive component of the current is much bigger, so it's going to have this steep angle when it's open circuit. Okay, but the magnitude is right. That's what we've given in the first place, 8 amps. All right.